and thanks for the opportunity, and thank you everyone for joining today. I'll just share my screen now. Okay. So this is working okay, Yue?
Yeah, perfect.
Brilliant. All right, well, hello everyone. My name is Tancrède. I'm a postdoctorate at the University of Lausanne, working with Guillaume Jouvet and this team of co-authors you can see here. And today I've been working on for the past 6 months, and which is about modeling the Alpine Ice Field in the European Alps using a new model called IGM, which uses physics-informed machine learning and trying to be more data consistent, basically. So as a small teaser to what comes further into the talk, you have here a map of ice surface velocity modeled by IGM during the LGM, so about 25,000 years ago, at 300-meter resolution. And so, okay, first slide about motivation. So why are we interested in modeling the Alpine Ice Field? More generally, throughout the rest of the talk, I'll be using this acronym called AIF quite a lot in the slides, which just refers to the Alpine Ice Field. So that's basically this thing you can see here, which we model in this case, which is the last ice field during the last glacial maximum that covered the European Alps. So this ice field has been studied extensively for more than a century in the Alps. People have been trying to constrain from empirical data former extent, former thickness, glacial erosion, flow direction, all kinds of interesting things, especially from the geomorphological side. However, there is only so far you can get with empirical data. There are some things that are simply impossible to reconstruct or very hard to reconstruct from empirical data. For example, what about the former basal conditions of the ice 20,000 years ago? What about the former ice velocities, softness, temperatures? What about glacial isostatic load and former equilibrium line altitudes? And what about glaciers that are merging and unzipping within the process? And so it's quite useful to use modeling for that. And in order to trust our models, we need to make them as data consistent as possible with the data that we have. And so a first step in this process understanding mechanism and studies is to really get a modeled Alpine Ice Field at the LGM that is consistent with the data that we have. And so that's where we've been having problems so far in the literature and the previous work. One of the reasons for that is that the last glacial maximum Alpine Ice Field, was topographically constrained. So this is why it's called an ice field and not an ice sheet, for example. And when you have a topographically constrained ice field, you have to resolve very fine topographies in order to model accurately ice extent, thickness, and velocity. So this is a picture of a modern day ice field in Patagonia. And you can clearly see it's very similar to what we would expect the Alps to look like 24,000 years ago. And you can see that the ice is being heavily controlled by topography. So it's the ice flux is pretty much entirely controlled by where the mountains are located, where the mountain ridges are located, where the valleys are located. And the hydrological basins will be very similar to the glacial catchments in this case. And the problem is that when we've been modeling the entire European Alpine Ice Field so far at the LGM, we've been restricted to resolutions of 1 to 2 kilometers. So the best models and the best studies have been restricted to 1 to 2 kilometers spatial resolutions. However, when you take a topography and you smooth it to 1 to 2 kilometers or you resample it, you get this smoothing effect, which completely modifies topography. I'm sure everyone here is very familiar with this. So here, if you draw a transect between A and B across the Chamonix Valley in the Mont Blanc Massif, you end up with this sort of cross-elevation profile graph. If you plot the resolution, if you plot the topography sampled at a resolution of 200 meters, you end up with this black line. And if you plot it with a topography that is resampled at 2 kilometers, which is what we've been running our models on, you end up with this red line here. And you can see that we are losing up to 500 meters of valley depth and up to 1,000 meters of mountain tops in some cases. And overall, your average surface slope is much lower. So it's going to be very difficult to model something that goes fast in deep valleys, that is really topographically constrained, that is accelerating in constrictions and narrowings and over deepened valleys, where you don't have this sort of steep topography and you end up with this very gentle topography. And so you can also see this in 3D a bit better. So if we put a camera here, which is just to the east of Zurich in the edge of eastern Switzerland, and we look southwest towards this main valley draining the Rhine catchment, you can sort of have a look at this topography in 3D. And so here we have the 30-meter topography on the bottom left panel. Here we have the 300-meter basal topography, which looks still okay. You can still see most of the ridges. However, it's still already starting to look a bit gentle. And then if you look at 2 kilometer, it's very smoothed out, and you lose all the detail about individual ridges, individual mountains. You can only just see the main valley. And so it's not surprising that it's particularly challenging to model over this type of topography. And so, as I've been saying, previous models have been restricted to that type of topography, 1 to 2 kilometers. Here you have the study of Seguino et al. 2018 on the right-hand side, showing a plot of misfit with trim lines, and the same plot for the study by Jouvet et al. In 2023. They both use a model called PISM, which is an ice sheet model over the entire Alps. And it's sort of the state-of-the-art simulations we had until right now in the Alps. And so what they did is they look at this compilation of trim lines from Kelly et al. Around the Rhone Valley near the Mont Blanc Massif. And they compared observed trimline elevations, which are assumed to represent the maximum surface ice elevations, against modeled maximum ice surface elevations. And the mean offset for this study is on average by 861 meter to thick with the model. And in this study, where they used a slightly better climate signal, you end up with an offset of 400 meters. So we still have, in the previous best studies, too thick ice by models by a mean on average of 400 to 900 meters of misfit. And the data is quite scattered as well. It's following an upward trend, but you really should be following a one-to-one line relationship. And we have quite a bit of scatter. And so the question that we asked with our work was, would we be able to reduce these model eta misfits just by using a model that allows us to model the Alpine Ice Field at much higher spatial resolution? Of course, in order to address this question, we need this model. So we need a 3D thermo-mechanical glacier evolution model. We need to model the entire Alpine Ice Field at less than 400 meter resolutions, as best as we can, really. We need to use higher order ice flow physics than what PISM uses, for example, the shallow ice approximation and shallow shelf approximation hybrid model. Because if you start to model really steep topographies, you really need something that takes into account both the vertical and horizontal components of the strain rate. And therefore you need high order physics. And ideally, you want to do all this at a lower computational cost in order to run many simulations and tweak parameters and explore your parameter space. And so now we are actually able to do this. So we have this new model called IGM, the Instructed Glacier Model. I'm going to quickly go through its components, but basically everything that has been developed over the past couple of years, IGM is quite recent, is now into this one slide. So every component of the system that you see shown here is part of IGM now. It's a module that you can plug in and use within your model. So we have an input climate that we can provide to the model that transforms it into accumulation and ablation. So that's the surface mass balance part. We have the enthalpy module, which controls the 3D temperature of the ice through the ice column. That has an impact on your ice flow and your ice thickness because it controls the temperature, but also the water content of the ice. It also impacts the basal sliding through controlling the basal temperature, how much meltwater ends up in the till and ends up reducing the pressure of the glacier on the bed. That's also influenced by geothermal heat flux. We have a glacial isostatic adjustment module that controls the amount of loading and unloading on the lithosphere from the weight of the ice. And we have an avalanche module also to redistribute snow and ice from very steep slopes, which becomes increasingly important when you start having high resolution topography. And then the ice flow module, of course, is the most important part, is what controls the ice thickness and what updates your velocity fields, and is what is traditionally the most expensive part. However, the peculiarity, if you want, of IGM is that now this ice flow part of the equation, if you want, is much faster. So instead of solving the equations numerically and traditionally on the central processing units, we solve them on the graphics processing unit, so GPU, thanks to machine learning. So basically, we train a physics-informed neural network, this PIN technology, to solve equations of ice flow physics. So we solve high-order 3D ice flow differential equations under the plateau-Pattern model, so high-order ice flow physics. And we train the neural network to solve these equations, and we can give the solution of these equations back to the neural network very frequently. So we can retrain it frequently through the simulation as it runs. And this convolutional neural network enables to parallelize the computation massively on a GPU. And so before we were only able to parallelize ice flow computation on a few number of cores, maybe 60 cores, 100 cores. Now we can parallelize on GPU across thousands of threads. And so we can compute this much faster, basically. And so the take-home message is that now we can model high-order ice flow physics with high fidelity and the same level of parameter control as before, but at a much lower computational cost. And so the result of this new tool is that we can model the entire Alpine ice field at 300-meter resolution. Here in this experiment, we run from 35,000 years ago to 18,000 years ago. So we bracket the full LGM period. You can see here a time series of modeled ice field volume for these 100 simulations. We have a grid size of this size, 3006 by 2006 for the modelers that are interested. And we can compute this in 2.5 days with this GPU. So just for comparison purposes, if we were to try to model the entire Alps with PISM, which was used by the previous studies at 300 meters, it would cost about 2.5 years of computation if you had 32 cores. With a very high performance computer, HPC, state of the art, it would still take you about 6 months based on our back of envelope calculations. And so here we can do it in 2.5 days, and we have multiple GPUs. So we end up running an ensemble in this study of 100 simulations at 300-meter resolution. And so the other improvements from previous studies is we have a glacial index climate signal, which is here, that modifies your climate from the LGM climate that you have closer to the pre-industrial climate through time based on an individual proxy record. And this proxy record is actually come from the Alps now. So we found some records that are more local and that produce really good results. And before that, studies were using records from Antarctic and Greenland ice core records. But I mean, it's quite problematic because it's quite far away from the Alps. And so now we were trying to find something a bit more local. And we have this avalanche scheme. And we also test different topographies in our model by removing or including valley field sediments. So there is a debate in the Alps concerning how much of those valley field sediments there was before the last glaciation, or was it all there, or was it eroded during each glacial cycle? So there's a lot of research around that. So we were interested to test. Okay, so this is our setup. Oh yeah, just one more slide to talk about these different parameters that we vary. So within our ensemble of 100 simulations, we vary 10 parameters that are being perturbated between these ranges of min and max values for each parameter. And the important thing to say here is that they come from different system components. So they influence different parts of the system. We have parameters that modify the sliding and the bed conditions of the glacier. We have parameters that modify the ice properties, the ice temperature, the surface mass balance in the climate, the basal topography, and the glacial isostatic adjustment. So they come from a very varied array of system components, if you want. Okay, so initial results from the ensemble. We have 100 simulations. Here you have time series on the left from 35,000 years ago to 18,000 years ago of modeled aerial extent. And you can see the LGM is around 25,000 years ago. That's when you have the maximum extent. And on the right, you have a GIF of maximum thickness time independent for each simulation. So each image in the GIF is a simulation amongst the ensemble. And you see the maximum thickness time independent, meaning every pixel is computed the maximum ice thickness throughout the simulation. So it shows you a snapshot of the LGM, last glacial maximum, across all regions, even though they don't necessarily reach the maximum extent at the same time. So now we have this ensemble, and we want to know what to do with it. So ideally, we want to isolate the ones that are the most data consistent, so that fit the extent and the thickness data that we have in the Alps the best. So how to do this? The idea is to do this as quantitatively as possible. You could do it by looking at it, like here on this GIF, but you could also try to actually measure it and give a score and sieve through these simulations, which is what we tried to do. So I'll just present the sieving procedure in detail here. So we have 3 sieves that allow us to go from 100 simulations down to 8 best simulations that we keep as a group of best simulations that we then do analysis on. And so the first sieve is really to score all these simulations against how they fit in terms of LGM ice extent. So what we do is we compute for each simulation. Here you have an example of a bad simulation and a very good simulation. We compute the LGM ice margin, which is shown in blue here, all these tiny blue pixels, which are between the ice and no ice masks. And we compute the number of pixels that overlap between these blue and the red outline, which is the mapped and dated LGM moraines around most outlet glaciers in the Alps by the empirical community over the past few decades. So we only select areas of good confidence in this, and then we compute the overlapping number of pixels, and that is transformed into a score normalized between 0 and 1. So the worst simulation in the ensemble is scoring 0, the best is scoring 1. And then we have a sieve that basically allows us to filter for the best simulations by only showing the simulations that are above 0.8 in score. So then you end up filtering quite a lot of simulations. I think we only keep 32 here in the light blue. And you then give those 32 simulations to the next sieve number 2, which here filters for the ice thickness fit with data. So what we do is we collected 353 trimline observations from around the Alps, as you can see on the left panel here, from literature. So we didn't actually do the observations ourselves. We collected that from previous work. And then we quality controlled them against high resolution digital elevation models, just to make sure that the reported elevations made sense with high resolution DEMS when it comes to their actual locations. We removed the outliers and we kept the 353 that were matching. And then what we do is we basically compare the elevations reported at those trimlines with the maximum modeled ice surface elevations through our simulations for all 100 simulations. And then we compute the mean misfit of that. And if the mean misfit is above 160 meters, as you can see here, then those simulations inherited from the previous sieve get filtered again. And so you end up with 12 simulations at the end. So these blue dots here, which are below both, they are above 0.8 in terms of score from the previous sieve, and they are also below 160 meters in mean misfit with the trimlines. Then we do the same for the standard deviation. So we don't want to just have a good mean misfit, but also less, we want to minimize the amount of scatter across the misfit. So we look at the standard deviation, make sure it's below 100 meters. And we end up with 10 simulations here. And then what we did is just a final visual check at those 10 simulations to look at how they match the empirical outlines. So similarly to what we were looking at in the GIFs earlier, but just with 10 simulations. And we looked at this with a few people and isolated 2 outliers that looked like they were not matching very well in the west and the north. And we end up with 8 simulations, which are called not ruled out yet simulations, NROYs. You'll see this acronym in the rest of the talk, which basically ends up being our 8 best simulations, which are indistinguishable equality and which we use for analysis later on. Okay, so results from this, now we have our best simulations from the ensemble, almost fully quantitatively. And we can look at how it compares with PISM and the previous 2 kilometer simulation of Jouvet et al., which was published in 2023. And so here on the left, you have the aerial extent modeled from 30 to 18,000 years ago. PISM, the black line, is the PISM 2 kilometer simulation by Jouvet et al. And then RN-ROYs, which are the 8 best simulations at 200 meters, are in this colored time series. And you see that we reach a very similar aerial extent, maybe a little bit more extensive throughout the entire Alpine Ice Field. However, in volume, we are much below. So we have a 35%, around 35% thinner Alpine Ice Fields, which is what we expected. So we were asking the question whether we were going to get a better fit with the trimlines with thinner ice field at higher resolution. And this is what we start to see here. So let's look at this in more detail. So if we look at the best fit simulation within those NROYs, number 37, it looks like this. The results are very similar across all the other 7 NROYs. I'll just show one of them here for visualization purposes. So if we look at the top right panel first, we here compare IGM at 300 meters for this best simulation and PISM at 2 kilometers, and we do a difference. And everywhere that it's blue is where IGM is thinner. you can see that we have thinner modeled ice across most of the ice field, on average by 230 meters, and in some places by up to 400, 500 meters thinner. For example, the Rhine glacier catchment and the Garda glacier catchment is where we have the most thinning. Now, if we look at the fit with the trim lines, here are our 353 observed trimline elevations compared against the modeled maximum surface elevation at the location of those trim lines. And ideally, we want a perfect fit to be within this line of 1-to-1. And actually, this black line, which is our linear regression fit, is very close to the 1-to-1 line. And the mean misfit is down to 132 meters for this specific simulation. The mean across all NROIs is 146 meters, so very close to this. And as a result, this is much thinner than previous work. It's between 2 and 4.5 times lower misfit in thickness than previous work of Jouvet et al. And Seguino. And also the spread is much less present. Actually, we have much more clustered data set around the 1-to-1 line. So we have a much better fit in thickness. One way to look at it is in 3D. So if we zoom into this area of thinning here, which is within the Rhine glacier catchment, we have this 3D view. So this is the same place that we were looking at earlier, the topography in 3D. We have the camera here looking southwest into this main valley draining the Rhine catchment. And here you have ice thickness for a PISM at 2 kilometers, and we keep the color map exactly the same. And if we switch to IGM at 300 meters, we end up with this. So I also plot a 30-meter DEM just as a reference elevation height. So if we go back to 2 kilometers, we see much less of the nunatack sticking out in this reference height compared to 300 meters. You also see the color is much less dark blue, which means that we have less ice thickness. We can also look at the ice surface velocity. So same place, PISM at 2 kilometers looks like this. You have a little bit more acceleration in the center here in this main valley, but it's not super obvious. If you switch to 300 meters, you end up with this, so much faster ice flow. So this is not surprising. Now we have much more highly resolved topographies, so we modeled at much higher resolution, which means that we have ice that is constrained into deeper valleys, narrower valleys with steeper sidewalls. And we have a lot of ice that is trying to fit into a smaller place, and so it has to accelerate mechanically if you want to respect conservation of mass. So this is called the Venturi effect. And it's really obvious here in this part of the ice field. So we have these constrictions and narrowings in the topography, which results in really high topography, really high velocity. For example, here and here, where you have all the way up to 1,800 meters of ice motion per year. This is surface velocity and not ice flux, because that's just looking at the surface. Okay, and so this was the fit in ice thickness story. We also have a slightly better fit in ice extent. So this is the look of the best fit simulation in terms of ice extent. And if you compare the modeled ice against the black outline, which is again this outline from the empirical community about where we think the LGM moraines are, and you can see the fit is relatively good in most outlet glaciers and in most regions. And on the right-hand side panel here, we just compare how it does compared to previous PISM simulation of Jouvet et al. At 2 kilometers. So where we have a plus means that we have a slightly better match with the outline. Where we have a minus is slightly worse than the previous work, and equal is very similar. And so you see there are quite a lot of pluses around. I mean, the previous simulation of Jouvet et al. Was already quite good, especially at 2 kilometers in terms of ice extent. But this new simulation is a little bit better still. And the reason for the thinning and the volume loss is basically shown here. So that's what we think is happening, is if you compare IGM and PISM both at 2 kilometers, you end up with a velocity difference that looks like this. So we have wherever it's red, IGM that is faster than PISM, and blue the opposite. And it's not super obvious that you have a speed up or a slowdown. It's pretty homogeneous. However, if you go to 300 meters versus 2 kilometers, so IGM at 300 meters here, you see that we have red in lots of places, especially in the narrow, deep valleys that drain very large catchments, some of the largest catchments. And this is what we were looking at in 3D earlier. We were looking at this area right here, which is the Rhine Glacier main valley. And what it shows is that you have speed ups and accelerations of flows where we have a lot of ice that is constrained by topography due to the higher resolution. And these also coincide with places where we have the thickest ice because we have the deepest valleys. And so overall, you end up with a signal of much less voluminous entire alpine ice field due to only a few places where you have much faster flow. And this has implications for subglacial erosion. So this is just plotting the subglacial erosion potential ratio between PISM and IGM. So we compute a subglacial erosion potential with a simple power law exponent of 234 from Hermann et al., for example. And then we just compute the ratio between PISM at 2 kilometer and IGM. And you see that every place where it's red, it means that we have faster basal velocities, which means that we can result in much more subglacial erosion. So this plot is only here to say that it's important that we model at high resolution also for understanding landscape evolution, quaternary valley incision by glacial processes at the ice field scale. And this new sort of high technology for being able to model at high resolution will enable to better quantify quaternary landscape evolution because of glacial processes. Other things that we can learn from this model is related to the first slide on the motivation is also some things like ice surface velocity, where you can plot, you can see on the plot here, but also basal ice temperature. So this is pressure adjusted basal ice temperature, showing you where you have cold-based ice throughout the LGM versus warm-based ice. And now we can resolve this in much higher resolution than before. And then on the right-hand side here, we can also look at the evolution of the equilibrium 9 altitudes through our simulation. So for example, here you see the ice accumulation area in blue with the magnitude of ice accumulation. And then the ablation area is shown as this color map of ice surface elevation. So where you get closer to the black, you get closer to 1,800 meters of ice surface elevation below the ELA. And when you get closer to yellow, you're closer to 800 meters of elevation below the ELA, which is in black, which is this line here. It's a slightly strange way of looking at things, but it really allows you to see the difference in ELAs through space. So for example, on the Jura side, we have quite low ELAs during the LGM, 750 meters ASL. However, in the Garda catchment, it goes all the way up to 1,800 meters. So we have more than 1,000 meter difference in ELAs within a single system, which really highlights differences in former climates such as precipitation and temperature. And so that's an interesting thing that we discuss in the paper and that we're quite interested because it has implications for understanding paleoclimates and landscape evolution in general. Okay, so I'm going to try to show you some videos to finish off just for the simulations. So this is ice thickness. Hopefully you can see this. Modeled for the entire simulation and for the entire Alps. And the time is here on the top. So you have the counter between, it starts at minus 35,000 years ago, and it will peak at 25,000 years ago during the LGM. And then you will see a slight retreat after that until 18,000 years ago. And so that allows you to see how different glaciers behave, how they are asynchronous between each other potentially. And you can see the places with the most thickness and generally the ice flux as well. And the next video is different. This one is just a teaser about work that is in progress. So we still use that same simulation that is modeled here. However, we added millions of particles to it. So that's another advantage of the GPU that I wanted to talk to you guys about, is that we can now actually seed millions of particles and it still fits in the GPU, which was almost impossible with traditional computing before this type of technology, which means that we can now track sediments through our glaciers. And so here I've done it for the entire Alps, but I only zoom on the Lyon area just because it's otherwise there's too much detail to see with the human eye. So you have the Mont Blanc Massif right here, and you have Lausanne and the Geneva Lake, and you have Lyon. And you will see ice surface velocity, and then you will see a lot of small particles being modeled. And so that's really nice because it allows us to now be able to study the formation of moraines, the re-entrainment of these sediments. It also is a really nice way of looking at the directionality of flux and the speed of flux. So you see where you have more yellow colors, you have also really fast particles. And sorry, you also see very well how different tributary glaciers join together and fight against each other, which one is pushing against the other one, and then how they re-entrain all these particles to finally deposit them into LGM moraines during the LGM. And then you can actually basically track where all the LGM sediments are coming from and where they were seeded from. And that has interesting implications for the provenance of erratics and what kind of rock types you're expected to find into specific LGM sediments or moraine deposits. And so this is not going to be published in this study. This particle stuff is very much work in progress, but I just wanted to show you because it's quite exciting to see that we can now create this geomorphology basically and model it and try to estimate it. Okay, so I just have one conclusion slide now, just to take home messages basically to say that now we have this newest version of IGM, which is a 3D thermomechanically coupled model. And we can model the entire Alpine ice field at the LGM at much higher resolution. So we've tested with this new GPU 200 meters and it fits. So we can go down to 200 meters for this sort of scale now. And we can do it at a much lower computational cost than before and with accurate and reliable results. And the result of using this new tool for us means that in the European Alps, the resulting fit with geological data is significantly improved, both in ice thickness and also in ice extent. And so a conclusion point as a more general, wider implications from this work is to say that high resolutions are likely a necessity to really make major step forward in modeling more accurate continental scale ice bodies, such as large ice fields or ice sheets like Greenland and Antarctica. And this computational bottleneck that we had with traditional computing for the past, 2 decades, basically, can now be overcome with GPU-based models and physics-informed machine learning, which is quite exciting. So now we see that we are on the brink of a new phase of computing for modeling in earth sciences in general using GPUs, which is really exciting because it really allows us to do more and new things and answer some exciting research questions. So yeah, I will stop here and thank you very much for listening, and I will take any question. I guess, should I stop sharing my screen or?
Yeah, so you can also keep it, Tancrède, because some people will refer to some slides.
Yeah, sure.
Yeah. Okay. So thank you a lot, Tancrède, for your great talk, which is super interesting. And I see there are questions in the chat and also people raise hands. Maybe first, okay. So there's a question from Mahanas. He or she asks, I wonder what's the black boundary in the GIFs and videos? Is that the LGM boundary?
Yes, exactly. So this line here probably refers to the question refers to this line here. So this is an outline that was initially drawn by a compilation of LGM ice extent from Ehlers et al. 2011, and it was since updated by people who studied LGM moraines and dated them in a series of locations. And so we used the most up-to-date update of the outline, which you can see here. And it has different levels of confidence. So there are places where we know where the moraines from the LGM are, and others where it's much more uncertain, which is why when we do our quantitative model data comparison, we sort of focus on the high confidence areas. But yeah, it's a good question. Thank you.
Okay, so there's a question from Yan, and he raised his hand. Yeah, Yan, how about you just speak?
Okay, thank you very much. Many congratulations, Tancrède. That's great stuff. The progress we've been waiting for a few years, I think. I've got 2 questions. A very simple one. You have a 25 Ka maximum for ice volume, which is the same as the maximum for the minimum for the temperature input. And I just wondered why there wasn't any time lag in the ice buildup. I might expect, maybe hundreds or 1,000 years time lag there.
Yes, that's a great question. So it relates to this. So here we have the ice volume for the 100 simulations. The LGM is not reached everywhere at the same time, but overall it's reached around 25,000 years ago. Actually, when we look at the max extent, it's closer to 24.8. And it's really related to this climate forcing curve that we use, which is from Lucio et al., which is speleothem record. And that glacial index really controls how much cooling we get at which time. And you can see that the climatic LGM, which is when this curve reaches its lowest value, is 25.1. So we have a little time lag of about 300 years in our model. But this is what was observed in previous modeling of the Alpine ice field, is that the time lag is very small compared to continental ice sheets. And actually, now that we have thinned the ice field, that is much thinner than before, we expect the timeline to be reduced, actually, because the ice field is able to be much more responsive when it comes to the ice volume transferring into ice extent, because there is less ice volume now. What we observe is when we modeled thicker ice sheets like Greenland or Antarctica, we then have much more time lag because of the enthalpy-induced memory and the inertia mechanisms. And sometimes we have 1,000-year time lags. But in the Alps now, what we think is happening is that because it's thinner than before in our previous models, we have much less time lag induced by memory of thermal temperature in the ice, basically.
Great, thank you very much. My more important question was about trim lines. And I don't regard trim lines as reliable evidence of the maximum height of the ice. They really just record the height of geomorphologically effective ice. So I think I would prefer your putting greater emphasis on the aerial extent than on the vertical extent as the trim lines might suggest.
Yeah, I mean, this has been a debate in a lot of regions in the world where the trim lines really truly represent the maximum ice surface. And what I think is happening is that in some parts of the world, they don't, and in others, they really do. And the empirical community in the Alps, which has been observing these trim lines and also dating LGM moraines, they were pretty convinced until, well, for the past decades, that trim lines were really actually good evidence of maximum ice surface elevation in the Alps. Because for the simple reason that we know the extent of the LGM from moraines, and we can calculate the ice surface elevation profiles, and the ice surface elevation profiles that make sense end up reaching the trim lines. And also, when we do this modeling, even if we don't see for the best fit simulations, so in this slide here, I show a lot of the same plots of fit of trim lines for random simulations within our ensemble. So here we don't actually filter for the simulations that fit the trim line best. And you can see that the fit is always pretty good. It's always a mean of less than 200 meters, and it's always along this one-to-one line. So what I mean here to show is that just by increasing the resolution, if we just model the Alps, not trying to filter for any simulation that does best at fitting those trim lines, we end up with a good fit with the trim lines in terms of just highlighting the maximum surface elevation. And on the left here, I've plotted the basal ice temperature at the location of these trim lines for the same random simulations. And what you would expect if you had a relationship between basal ice temperature and the formation of trim lines, which is the debate, then you would probably expect a bit more of a cluster around the blue line, which is the -2 degree temperature, which is the switch between cold-based and warm-based ice. And here we don't see this. We see a big cluster, a big scatter of points at all kinds of temperatures. This is the maximum temperature at the LGM modeled by the model. And so what I mean to say here is that we end up with a good fit regardless of what we do, just by increasing the model resolution. And so this goes in line with what the empirical community has been saying in the Alps for a while. And the debate that was existing in the Alps until now was more related to actually previous usage of coarse models that were way too thick. And therefore, people that were using these models were utilizing the debates from other regions like Scandinavia and the UK to say, oh, maybe it's the same in the Alps, maybe it's a thermal boundary, it's not the ice surface maximum elevation. But I think now, and I'm pretty convinced by this, was the result of our previous models being too coarse resolution and too thick as a result. So I totally agree with you, except I think that now I'm pretty convinced that in the Alps, the trim lines are decent observations of maximum ice surface elevation. The challenge is more...
Thank you very much.
Yes, but I think the challenge also is more which date does it correspond to? Is it the actual LGM or previous quaternary maxima? And that's a much more challenging question to answer because it's very, very hard to date these trim lines. Yeah.
Thank you.
All right. I did hear. So could you read another question?
Oh, yeah. So there's a question by Trevor, and he says that there seems to be hundreds of nunatucks at the LGM. Can you model to evolution of ice-damped lakes during deglaciation?
Oh yeah, that would be super cool. Yeah, that's a great question. At the moment, we don't have a proglacial lake module in IGM, which is quite a recent model. This is something that I would like to develop actually, because in order to, for example, model the deglaciation of the Alps, we would really need to have proglacial lakes to get the retreat rates right. So I don't think they are too important for the dynamics of the LGM, but they would be super important for the deglaciation. And so if you have such a module, then you would be able to model them anywhere you have ice damming a depression in topography. And so you would end up with proglacial lakes all over this topography whenever you have a depression. That would be super, super cool. But the answer, unfortunately, is no, we can't do that right now with IGM. But it should be possible. We just have to develop it and find the time to do it. Because proglacial lake modules are now implemented in a range of different models. And so we need to follow that trend and start using them for sure.
Right. Okay, we have another question from Pratik. And the question is, what is the physical basis to the rate of seeding? Are they similar to valley wall rock input to the glacials? Where do you get the data for that period?
Yeah, it's a great question. So the video that I showed is very, very basic seeding, nothing realistic. It was just to do a first simulation with IGM to test it and see whether it works and whether we can model millions of particles computationally feasible. However, now this is not what we're going to do in the study. I'm thinking of a much more realistic seeding. And so I'm trying to divide my seeding into superglacial seeding, so mimicking rockfall, and subglacial seeding, mimicking subglacial erosion, which will be based on velocity. And so for the superglacial seeding, what you can do is decide on a threshold of slope angle. So you can decide maybe, let's take a certain slope angle after which you start getting some rockfall. You can control the frequency and the density of that in a random way. And so I haven't made decisions on these numbers, but yeah, you're totally right. We will need to look at literature based on rates of rockfall for different lithologies, different regions, try to mimic that in a model. However, we'll have to make some pretty crude estimations of that. I think it won't influence too much the trajectories as long as you seed densely and frequently enough. But you can totally control that. It's some of the parameters we have. In the simulation that you saw, I was only seeding every 100 years, and I was only seeding every 5 pixels, so a pretty low density. But I think we've tried and it works to seed almost every 2 pixels, so really high density. And then for the subglacial seeding, we'll have to try to mimic some kind of subglacial erosion relationship with basal velocities. So hopefully find a relationship for different lithologies as well and different settings and a frequency and density that works for that. So we can track particles in 3D through the ice column, but some that come from the superglacial origin and some that come from the base of the glacier.
Oh, thank you. So we go on. So lots of questions. So there's a question by Jing Tang, and he says that so you have reconstructed the ice extent to evaluate the performance of your model. Have you incorporated the uncertainty of age and the extent in your model?
That's a great question. So the answer is basically no. So how can I show this? I think it's this one. So in this study, we score against ice extent and ice thickness in a time-independent way. So all we want to do is to be able to reproduce the right geometry with the climate forcing that we get. And the timing of our LGM is only really constrained by the climate forcing that we get. If we were to use different climate forcings, maybe multiple curves of climate records, we would end up with different timings. And we don't compare the timing of individual glacier against the timing of individual moraines. So what we do to get this map is to compute the maximum ice thickness and therefore ice extent. in each pixel throughout the entire simulation, which is why we call it time independent, which means that this is a snapshot of the LGM which has no time associated with it. So for example, in the Lyon area, the maximum extent could have been reached at 24,000, but in the Rhine, it could have been 500 years later. Actually, I have a map here which shows you the timings of different LGMs. So this figure here, you have a graph for each of the dots that are shown on the plot here for each of the main outlet glaciers around the Alps. And you see the timing of the LGM. This is ice thickness normalized. It's slightly different for each glacier. I mean, we have a very consistent LGM across most glaciers at 25.1. And then we have some glaciers that have a bit more inertia, the big ones like the Rhône glacier and the Lyon. And we have some that are a bit earlier because they are even smaller and even more reactive, like the Dora Baltea, Dora Riparia. So, but this is a result of our study, but it's not something that we test against. It would be another step in future work to force your ensemble with multiple climate records and then score against the timing. And this is something we're interested in doing in our project. So I'm working as part of a project called Reconcile, which hires another postdoc, Sarah Kamleitner, and another PhD, Andreas Hens. And Sarah is working on a database across the Alps called Alpice, which will be a database of geochronological evidence and geomorphological evidence that will allow us to calibrate our models in time and space. And so we will really be able to score each simulation against the timing as well, how our time and uncertainty in time is fitting actual dating data. But in this specific study, that was not the scope, and we haven't done it that way.
Yeah, very cool. Okay, we have a question from Bernard. The question is, what's the magnitude of the isostatic rebound since the LGM in your model?
Yes, thanks you. That's a great question. Yeah, so it's a bit less than before because we have thinner ice field and therefore less volume. So this is the maximum deflection of the bed modeled by our isostatic module during the LGM for each of the 8 best simulations. So these are the NROIs that we keep at the end of our model data comparison procedure. And you can see there is a bit of variability, but actually most of them are around 100 to 120 meters, 140 meters at max of bed deflection. This is a little bit less than what was modeled before by for example, Jürgen May and Guillaume Jouvet and Julien Saguineau, which was more in the range of 150 to 250 meters. And so this has potential implications. I mean, this is not necessarily the true answer. We could be wrong with that, but it's just a consequence of the fact that we have less ice volume. And it could have implications on the contribution of the post-glacial rebound on the present-day uplift rates of the Alps, which is still under debate. And so using this work could provide some answers to that in future studies, potentially.
Thank you. There's a question by Andreas. He says that you mentioned the test regarding the removal of valley fill sediments in the modeling. What is the difference between the results of including or excluding estimated volumes of valley fill sediments, as some big alpine valleys are filled with large thickness of sediments of partly unknown age?
Yes, the questions are all incredibly good. Thank you so much. We've done a sensitivity analysis of that, and I was really interested to see whether it would create a big difference. So what you see here is time series of areal extent and ice volume for the best fit simulation, the one that really scores the best, number 37. But we rerun it with and without the valley fill sediments. So by that, I mean that we run it with a DEM that is just glaciers and lakes removed. And in the second case, we also removed the valley fill sediments using the DM that was produced by Jürgen May in the 2016 paper. Thanks, Jürgen, for sending that DM to us, by the way. And here you can see the blue and the orange line are very close together. We almost see no difference. This is, time series of the entire Alpine ice field. When you look at the map, I mean, here they're quite small, but the difference are very, very small in terms of ice extent and fit with the outline. Of course, you see difference within the valleys where you have much more dark red because we have much thicker ice in the valleys where we have removed the sediments. And in terms of fit with the actual ice surface elevation and the trim lines, it's quite similar. So without the valley field sediments, which is on the left, we had 132 meters of misfit. And with, we have 159. So the mean misfit is quite close. And you can see that the fit with the trim line is still good. And in fact, within our 8 best simulations, we have 2 that are as good as number 37, which were modeled without the valley field sediments. So these are the 2 extreme cases of pre-LGM conditions, right? The full volume of valley field sediments and the whole volume removed. And we still get to very similar results. The truth, it was probably somewhere in the middle and at different ranges between different valleys, but the impact on our model is quite minimal, which means that basically when you remove these sediments, the ice fills the depression very easily in our model, and then you get to the same extent and the same thickness very similarly when you model after that, which means that actually when we do this modeling, we can afford to be inaccurate with the amount of sediment that we estimate from these valley fields. It won't impact massively the results in terms of ice extent and thickness, at least. However, if you want to get the ice thickness right in individual locations like the Rhone Valley or the Martigny segment, where you have lots of valley field sediments, then of course you have to estimate the volume of sediments before the last glacial maximum properly. But yeah, it's a great question. But basically, yes, the impact is very small for the nature of the work that we do in this study.
Right, thank you. So there's a question from Dennis. He asks, instead of using hypercubes to select parameter values and then find the best simulation, have you thought about a parameter estimation model such as PASS or MASS?
I'm not aware of these models, actually. I'd be very interested to talk more to you about that. Maybe if you could send me an email, that would be fantastic. I'd be very keen to look into it. I've been using latent hypercube for the past few studies I've done on ensembles because, to be honest, I'm not a statistician or mathematician, so I've been trusting other people in the field doing that. For example, the work of Ash van den and Thorsten Albrecht in Antarctica using ensembles for modeling Antarctic and Greenland ice sheets. And they've been using latent hypercube, claiming that it was the most adapted at the time algorithm for sampling as homogeneously as possible. However, I'm not a mathematician or statistician, so I don't pretend to know which one is best, which technique is best for sampling parameter spaces. I think the fact that we have such a high dimensionality parameter space with so many parameters we want to vary, but so few simulations we can run because it's computationally expensive, means that regardless of which algorithm you choose for sampling, you're going to end up with missing a lot of space in your parameter space. And so more importantly than which algorithm you use, I think the most important is to be able to model as many simulations as possible and to really increase the size of your ensemble. And here with a tool like IGM, because it's much cheaper to run a simulation now, we can really increase the size of the ensembles, which means that we can explore the parameter space better. But yeah, I mean, I'm all ears to hear about potential new algorithms that are exciting to explore parameter spaces. And if you can send me an email about that, I'll be very interested to chat more.
I have a couple of questions. This is Bernard Helle. And first of all, though, I want to really applaud your presentation and also this introduction to quite an exciting new phase of modeling. And but my questions kind of involve two extremes of your talk. At the beginning, perhaps I missed this, but tell us a bit more about the climate forcing and how it responds and is updated as the ice grows over the Alps. And then secondly, I'd like to also, if you could say just a few words about your particle tracking that you introduced at the very end of your talk.
Yeah, thank you so much. Yeah, I'll go back to the slide with the climate. So yeah, I haven't managed to really talk about the climate that much because of time, but thanks for the question. So the climate that we use are two snapshots in time. One is they are both from a regional climate model study that was published in 2024 by Emmanuel Rousseau et al. So colleagues of us at Bern, which basically re-downscales a global circulation model into a regional climate model at 2 kilometers over the Alps. And it's so expensive to run these climate models that they only do it for a specific snapshot in time. So we have basically we have a map of LGM climate from temperature, precipitation, all kinds of variables, the variability of temperature through the year and through the days. But we have this only for the LGM and also for the pre-industrial. And then what we do with this curve here and this glacial index scheme is to switch from one map to the next, but only following the magnitude of change that you can see in other proxy records. So instead of doing a linear interpolation, you follow the wiggles from another proxy record. And this other proxy record traditionally was for studies in the Alps using Greenland and Antarctic ice cores. And here we found some records that are trying to capture a more local climate. For example, the speleothem record you can see here from the Jura and from Siebenhengste, which is, sorry, in the Swiss Alps. And so, yeah, we have an actual map of precipitation, temperature varying through time, but only for the LGM. And it's basically being modified along this signal here. And so when you get closer to 1 in this glacial index value, you get towards more this LGM map. When you get closer to 0, you get much closer to this pre-industrial map. So if you want, this curve is just, okay, how close do we get to the LGM climate versus the pre-industrial climate, basically. So that's for the climate forcing. And it's not work that we've done in this study. It was work that was really developed by the colleagues at Bern. There's several papers about this simulation of the climate in the Alps. And it was used by Jouvet et al. In 2023. It's really this climate that really enabled to get a better fit and extent during the LGM compared to the Seguino et al. Paper, which was using present-day climate and then perturbating it with this glacial index climate. So this new climate of the LGM is really improved the fit and extent, and it's why the PISM simulation of Guillaume Jouvet was already really good in extent. So yeah, it's a key question you asked, because basically being able to produce really good regional climate model estimations of paleoclimate is a key component of this work, and it's very important to get a good fit. You can model as high resolution as you want. If you don't have the right climate, you're going to get complete misfit. And so, yeah, it's great that I have the opportunity
of course, to nest, a really high resolution model that you could update the climate as the ice grows. And because, I mean, you're talking about a kilometer or two of ice, it's bound to have an important impact on that climate, the local climate.
Yeah, totally. Absolutely. I mean, there's definitely still some biases in the climate that we use. And one of the ways to remove those biases is to have the whole thing fully coupled, like you say. That would be incredible. That's definitely the next step for the next few years.
The future.
But I'm very interested to work on that. Would love to be able to couple IGM to climate models and have the two running together. And your other question was about the particle tracking.
Right.
So basically now, what do you want to know more about how we seek them or how we model them, or? Well,
I'd like to know kind of what are some of the results that you didn't want to show us earlier, but maybe you don't want to do it now, but I look forward to seeing them.
Yeah. I mean, the study just started on that, really. And the idea is to just look at the provenance and the transport pathways of LGM sediments throughout the Alps. So the idea is, if you take a polygon of Mont Blanc granite or a specific lithology from a specific catchment, then you can ask a code to look at all the transport pathways of particles that are being modeled by the ice model through the entire LGM. So you can ask the question, okay, where are all the possible locations that the Mont Blanc granite could go to during the simulation of the LGM? And reversely, you can ask the question for sink to source by saying, okay, let's look at moraine of the LGM, for example, in the Lyon area of the Rhone glacier, and let's look at all the particles that end up in this moraine, and let's ask the question, where could it have possibly come from, and plot all the trajectories that you've modeled in the simulation. And so this study is really just about doing that. Of course, there's a million other research questions we could ask with these particles, because we can actually see moraines being built, and we could compare the volumes of sediments against the one that we find. But yeah, I think there's a lot to try to answer. So I think I might just focus on the provenance story for now, on the trajectories, because it's the obvious starting point. But yeah, I think the particles are really opening a door of very exciting research we can do in terms of model data comparison between empirical sedimentology and dating and mapping of glacial geomorphology, but also of the modeling world now. We can bridge the two thanks to these particles. So it'll be exciting for sure.
Well, thank you. Thank you. And lastly, I'll just mention that these two questions that I asked are actually quite related, because I remember, I mean, this is a vague recollection that, and perhaps Donico and others know more about this, but there's some older simulations, and the test on the simulations was actually looking at particle tracking and getting, you know, distant traveled sort of radix in the right places. And it seemed to matter which climate model you actually forced. I mean, so if you actually had more precipitation on the west side, for example, that made a big difference. And so I think that, you know, the erratics are likely to be a kind of a key to working out exactly what was driving the ice, and also just, you know, inform the model more. But I repeat the fact that I'm really impressed with your talk, and it does really open up, you know, kind of a first view of this new age of modeling. So thank you very much.
Well, thanks a lot. Thanks for your questions.
Okay, all right. We have one last question, given the time also. The question is from Trevor. He asked, when you extend the model to cover deglaciation fully, would you kindly apply it to Britain and to Scandinavia? Yes,
yeah, so for the Alps and the deglaciation, this is something we want to do within the project and with my colleagues that I work with. Especially Andreas Hens, who's a PhD student on the project, who's quite keen to do model data comparison of this simulation from the LGM to the present day, so capturing the entire deglaciation and the Holocene, but against this new database of dates and geomorphology from around the Alps that Sarah Kamleitner is compiling. And so I'm very excited about this database, because when we have it, we'll be able to really do quantitative scoring of our simulations, both in space and time. Like has been done for the Brit Ice project, for example, in the UK, or with a dated project of the Eurasian ice sheet. Regarding the second part of the question, that will have to wait a little bit, because IGM is not quite ready for marine terminating ice sheets yet at the moment. So this is something that Guillaume wants to develop actively and has recently received a grant on. So he's if anyone is interested to do a postdoc on this, there is currently a job for a 3-year postdoc to develop IGM for marine terminating ice sheets. And so once that happens, which I'm sure it will in the next couple of years, we will be able to apply this technique to other ice sheets around the world that have marine terminating margins, like Eurasian ice sheet, British Irish ice sheet, or present day ice sheets like in Greenland and Antarctica. And hopefully that will bring some new answers to some research questions in these regions as well. So that's going to be exciting, but it's not ready right now, unfortunately.
All right. Okay, thank you, Tancrède. We have no more questions, and there are people in the chat saying, so they will get in touch with you for more questions. And
Brilliant.
So, yeah, so this is a very exciting topic, and I hope you can get more cooperation with the audience. And given the time, given the time, we have to finish our seminar today. And I thank you for the great talk, and thank you for everyone for attending. Yes, hopefully we'll see you next week for the next seminar. Yeah.
Sounds good. Yeah, thanks a lot, Yue and Aditi, for organizing everything and taking care of the talk. And thanks everyone for joining. All right.
Yeah.
Okay.
Thank you.
Bye.
Thanks, Tancrède. Bye.
Bye.